Today we're looking at lesson 4.05. May I have more, please? Today's objective is, given a story, I can write and solve an inequality in 2 out of 2 problems. So in yesterday's lesson, we looked at just rules of inequalities and how to solve inequalities. Now we're going to look at stories that have us set up inequalities and then solve them. But before we get started with that, we're going to look at some phrases, and we're going to ask which inequality matches each phrase. So we're just going to look at some phrases in isolation outside of stories and see if we can figure out what they mean in terms of inequalities. So we're going to start with more than 7. Which one of these shows more than 7? X is more than 7. Well, more than is going to be the bigger side, right? If we say X is more than, so that means our alligator is going to be chomping X, right? Because X is bigger. So it looks like this one will be our option. Let's look and see if that's the answer. It is. X is more than 7. We also read this as X is greater than 7. That's typically what we call this symbol right here is a greater than symbol. So X is greater than 7 means the same thing as more than 7. So let's look at the next one. How about no more than 7? So this is just like the last one, but now we've added this no to the front of it. So this one was more than 7. If we say no more than 7, that means we're going to include everything else. So we're basically taking the opposite sign, which is this one down here. See, everything that isn't greater than is going to be less than or equal to. See how this one doesn't include equal? So this one includes the opposite, all the opposite numbers. So no more than 7 is going to be less than or equal to 7. There we go. Let's look at the next one. A minimum of 7. Which one of these shows a minimum of 7? Think about what minimum means. It is this one over here. So minimum means the smallest value, right? Smallest. So our alligator is going to ignore our small value. Alligator always wants to eat the bigger one. Chomp, chomp. So this side is going to be the bigger side. And when we say a minimum of 7, we ask, do we include 7? Well, one way we can figure this out is we can say 7 is ... a minimum of 7. And does that make sense? 7 is a minimum of 7. Yeah, sure. That works. So we do include it. We do have that equal sign. 7 is a minimum of 7. Okay. How about the opposite side? A maximum of 7. Think about, is 7 going to be bigger or smaller? And is it going to be included? Seven is the maximum. That means it's the bigger term, right? 7 is the top term. So 7 is going to be bigger in this case. Alligator eats the bigger term, eats the 7. And for the same reason as the last one, we do include that 7. 7 is a maximum of 7. That works. Okay, how about at least 7? Think, is 7 the small term or the big term when we say at least? And then think, do we include it? Seven is the small term. So we say 7 is at least 7. That makes sense. We can also think about larger numbers. Say 9 is at least 7. Yep, that makes sense. What about 3? Let's do a smaller number. 3 is at least 7. That one doesn't work. So we're not going below 7. We're doing 7 and everything above it. That means X, all these numbers that we're choosing are going to be the bigger term. Alligator's going to eat that side. Okay, no less than 7. Now we have that no term again. Remember, if we figure out the rest of it, if we figure out less than 7, we need to go find the opposite term. So which one shows less than 7? And then go diagonal to find the answer when we say no, no less than 7. If you chose this one is less than 7, then we go this direction and get no less than 7. No less than 7 is going to be greater than or equal to 7. Once again, we can put in these numbers and say 7 is no less than 7. That's true. Can we say 8 is no less than 7? Yeah, that's true. 8 is not less than 7. What about 1? 1 is no less than 7? Doesn't work. So that's a good way to check that our answers are correct. 7 and 8 fit over here, but 1 does not. Okay, how about cannot exceed 7? Now this one doesn't say not, but it does have this cannot, which sounds like a not. So maybe we'll do the same process. Figure out which one says exceed 7, and then take the opposite. Which one says exceed 7? Exceed means bigger, right? Exceed is a term for bigger. So this would be our x is bigger than 7 or greater than 7. To do the cannot, we'll go the opposite. Take the opposite term and get x is less than or equal to 7. And fewer than 7. Which one of these shows fewer than 7? There we go. Fewer is a similar term to less. Less than 7 means the same thing. So x is less than 7. X is the smaller term. That is the correct inequality for this phrase. Great job on all of those. So now we're going to apply some of those phrases. We're going to look at some stories and try to figure out how to answer these questions with inequalities. We're going to use this method where we highlight the numbers. We ask, what are we trying to find, and then assign our variable, and then we will set up an inequality. Let's see how that works. So Elvira, we've talked about Elvira previously in some lessons in this unit. Elvira, the cafeteria manager, needs to be careful with her spending, and she manages the cafeteria budget so that they can serve the best food at the lowest cost. To do this, Elvira keeps good records and analyzes all of her budgets. So we need to write and solve an inequality for this situation. Let's see if we can get that on screen. There we go. Elvira's cafeteria serves milk with lunches. The milk supplier charges 35 cents per carton of milk, in addition to a delivery charge of $75. What is the maximum number of milk cartons that Elvira can buy if she has budgeted $500 for milk? So our first step over here says highlight the numbers. Where do we see numbers in here? Let's see, it looks like we have one there, and one there. These look like dollars. These are all in dollars. And our next thing is we're going to ask, what are we trying to find? Let's look at the question again. What is the maximum number of milk cartons that Elvira can buy? So that sounds like what we're looking for though. There, the maximum number of milk cartons. So that's our variable. We need to assign a variable there. Maybe let's call them C. C for milk cartons. So we just assigned a variable. And our last step is to set up the inequality and then solve it. So let's see, how would we set this up? They charge 35 cents per carton of milk in addition to a delivery charge of $75. That addition kind of gives us a hint of one of the operations that's going to happen here. Addition is actually an operation, right? That's add. That's a plus sign. So I think we're going to have a plus in there. We have a delivery charge of $75, so maybe we're going to add 75 to something. And then we have $0.35, or what we call 35 cents, per carton of milk. So if we have 1 carton of milk, that'll be 35 cents. If we have 2 cartons, that'll be 70 cents. If we have 3 cartons, that'll be $1.05. And what we're doing there is we're multiplying. We're multiplying this cost per carton times the number of cartons. But look, we said the number of cartons, we assigned a variable there, that's C. So if we want to do the total cost of these cartons of milk, it'd be the price per carton times the number of cartons. And then we also have a delivery charge that gets tacked on. Now, on the other side of this equation, or it's not actually an equation, but on the other side of this inequality, we know that Elvira has budgeted $500 for milk. And now the last thing we need to do is figure out what direction does this inequality go? Well, let's see, the maximum number of milk cartons. So we know that she can't spend more than $500, right? So if this is how much she's spending, it has to be less than or equal to $500. So that's how we get the inequality. It's less than or equal to. Now we know how to solve this, right? We've solved things like this before. We circle our variable. We highlight our other terms on the same side. And then we do inverse operations to get rid of them. We take the one that's furthest away from C, so that's 75 in this case. We're going to do the inverse operation, subtract 75 from each side. Those 75s cancel, we get 0.35C. On this side, we get 500 minus 75 is 425. And then we do not flip the sign. We only subtracted, and subtraction is not a case where we flip the sign. Our next step is to get rid of this 0.35. We are multiplying here, so our inverse operation will be to divide. Divide by 0.35 on both sides. These terms cancel. We divided by a positive, so once again we do not flip the sign. And I'll need my calculator for this. 425 divided by 0.35 is, I get 1214.285 ... Before we move on, let's do a quick review of times when we flip the sign. There were 3 of them we talked about. And we'll need to remember these in case we need to use them once we solve them. So there are 3 cases. One is when we multiply by a negative number. One was when we divide by a negative number. And the last one, which might be new, we might not think of all the time, but we did talk about it, is when we swap sides. Remember, if we wanted to move this over here and this over here, we would also need to flip the sign. So those are the 3 cases when we're solving that we need to be aware of, that we need to flip the sign. Okay, so we didn't need to flip the sign in this case. We got C is less than or equal to 1214.285 ... Number goes on. Okay, so we've summarized this up here. We use the variable m in this case. M is less than or equal to 1214.29. How would we describe this answer in words? So this was a story problem, right? They actually asked us a question. What is the maximum number of milk cartons that Elvira can buy if she has budgeted $500 for milk? So if M represents number of milk cartons, we know that the number of milk cartons has to be less than or equal to 1,214. Now this decimal is not going to make sense, right? Because we can't buy 0.29 milk carton. So we would say she can buy up to 1,214 cartons of milk to stay within her budget. And now it asks, can we write this answer in interval notation? Oh, now we have to think back to interval notation. We haven't looked at that for a little while. So interval notation, we previously talked about it in terms of a graph, right? We talked about domain and range in interval notation. But we can also use it for inequalities because we know this is the upper bound, right? We know this is the largest number. You can see the alligator eats it. So this is the largest number. 1214 is going to be our second number. We include it because of that equal sign. So we get square brackets. But now we have to ask ourselves in the context of this story, what is the lower bound? What is the minimum number of cartons of milk you can buy? And so you could buy one carton of milk. You could buy 0, you could just not put an order in. Can you buy -1 cartons of milk? That would be like returning something, right? You'd have to give them something. That's what buying -1 would mean. But I don't think they're going to let us return milk. So maybe negative numbers don't work for this case. Maybe our bottom value is 0. We could buy 0, we could buy up to 1,214, or we could buy any number of cartons in between. So that's how we write the answer in interval notation. Let's look at another story. So we're going to set this up as an inequality and solve it. The prices on many of the cafeteria foods change during the year. Elvira finds that she has ordered veggie burgers 4 times and paid $78, $72, $87, and $90 on the orders. To stay within her budget, Elvira needs to be sure that the average order of veggie burgers is not more than $82. How much can she spend on the 5th order to keep the average order within her budget? All right, our step number 1 here, we're going to highlight the numbers. Here we go. There's a number, there's a number, there's a number, there's a number. Lots of numbers in this one. There's a number. In fact, this is kind of a number, 5th order. And as long as we're highlighting, we might as well note that there's some interesting words here. The average order, we've talked about the average order a couple of times in this problem. I think we may have to remember what an average is. Let's talk about that in a second. But first, let's go to step 2 here. What are we trying to find? Let's go find our question in this problem. How much can she spend on the 5th order to keep the average order within her budget? So how much can she spend? That's going to be our variable. We need to answer that question with a variable. So let's give it a letter. Maybe V, like V for veggie burger. How much can she spend on veggie burgers on that 5th order? Okay, so we did that step. We did that step. Now we just have step number 3. We need to set up the inequality. Okay, so average order. We need to remember what an average is. What is an average? Well, an average, we've talked about a long time ago, was the sum of several things over the count of them. So when we're talking about an average of 5 orders, it'll be this one plus this one plus this one plus this one plus this one, we don't know how much it is. It's a variable, but it's some number in there. So it's adding all 5 of those together, and then we divide it by 5, because there are 5 of them. That's the count. So we get 78 plus 72 plus 87 plus 90 plus that last one we don't know, v, all over 5. Now, how much can she spend on the 5th order to keep the average order within her budget? The average order of veggie burgers is not more than $82. That sounds like one of those terms we used at the beginning of class, not more than. So think on that for a second, what direction that's going to go. We know 82 is going to be on the opposite side of this. What direction should this inequality go? Is 82 bigger or smaller than the average order? Well, we said if it was more than, that'd be easy, right? The average order is more than $82. Because there's our average order. Average order is more than, bigger side, crocodile eats it, alligator eats it. But this is not more than. So we're going to do that opposite thing. We're going to go across and take the opposite sign, which is less than or equal to. And that makes sense conceptually as well. The order is not more than 82. It's less than or equal to 82. That makes sense. We're not going over our budget. Okay, so let's solve this now. We have set up the inequality. We are ready to solve now. So it looks like I have a bunch of addition up here, a bunch of numbers to add. I can simplify that. Let me just get out my calculator. 78 plus 72 plus 87 plus 90. I get 327. 327 plus v over 5. This was simplifying. Don't need to flip the sign when we simplify. There were only 3 cases, right? Multiply by a negative, divide by a negative, swap sides. Okay, so if we circle our variable in our mind, highlight our other terms, which term on the same side is furthest away from v? We're going to get rid of that one first. We're dividing by 5, so now we're going to multiply both sides by 5. It's the inverse operation of divide. We get 327 plus v. We multiplied by a positive number, so we don't flip the sign. On this side, we get 82 times 5, which is 410. And our last step is to subtract 327. That's the inverse operation of add. These 327s cancel. We get v is less than or equal to 410 minus 327 is 83. So there's our answer. V is less than or equal to 80. Oops. Let's bring that back. V is less than or equal to 83. So there's a summary again of what we just did. That was the equation or the inequality we set up, and that's the answer we got. How would we describe this in words? Well, once again, this answers the question, how much can she spend on the 5th order to keep the average order within her budget? So she can spend less than or equal to $83. Less than or equal to $83 to stay within the budget. And can we write this in interval notation? Sure we can. 83 is our top value again. That's our alligator big side. So 83 is our second value. We include it because of that equal sign. So we have square brackets. Now once again, let's think about our lower bound. We could order $1 in veggie burgers. We could order $0 in veggie burgers. We could just not order them. Could we order -$1? Well, once again, that sounds like a return. It sounds like we're giving them veggie burgers back and they're supposed to give us dollars. And I don't think they haven't told us they take returns, so maybe 0 is our lower bound. Maybe the lowest number of veggie burgers we can order is 0. 0 to 83. All right, we have one more of these problems to do today. So students love putting ranch dressing on everything. So Elvira needs to keep plenty in stock. The students eat about 2.25 gallons of ranch each day. Elvira started the school year with 130 gallons of ranch dressing. She needs to have at least 20 gallons left when she reorders to have enough in stock until the new order comes. How many days will her ranch dressing supply last before she needs to reorder? Go ahead and pause the video. See if you can set up an inequality using these steps, and then solve it. Then come back to the video, see if you get the same answer I do. So first step here, we're going to highlight the numbers. We have a number there. We have a number there. We have a number there. These all look like they're gallons, so that's good. You might also notice some other helpful things, like we started the school year with 130. Also, the students are eating 2.25 gallons of ranch. So maybe that indicates we're losing it. Like this might be a negative number, negative 2.25. Okay, so those are some interesting things that might be useful to us when setting up our inequality. We have done step 1 here. Let's look at step 2. Ask, what are we trying to find? How many days will her ranch dressing supply last before she needs to reorder? How many days is what we need to answer. So that's our variable. Maybe let's call it D for days. All right, and our last step here is to set up the inequality and then solve. So we started with 130. So maybe it makes sense to just start with 130 like that. And the students eat about 2.25 gallons each day. So if this is each day, then we're going to multiply it by the number of days. This is going to be minus 2.25 times the number of days, which we said was D. Then we have an inequality that goes some direction we haven't determined yet. And we know that after all of this ranch has been eaten, we need to have at least, there's a term that tells us this inequality, at least 20 gallons left. So 20 must be our number on the other side. And we need to figure out which direction this points. At least 20 gallons. Well, we know we could have 20 gallons, so we'll have that equal sign in there. And then the minimum amount would be 20, right? We can't go under 20. So that means 20 must be the smaller side. This is how much we have left. It needs to be more than 20, so this is more than 20. Alligator eats the bigger side. All right, now we solve this like normal. We circle our variable, highlight our other terms. Do the inverse operations to get rid of our other terms. We'll subtract 130 because that one is further away than the negative 2.25. Negative 2.25D is greater than or equal to, this will be negative 110. We do not flip the sign because subtraction isn't one of the cases where we do that. Now we're going to divide, because we're multiplying here, so we're going to divide by negative 2.25. Divide by negative 2.25. These will cancel, but notice, this is one of those special cases. We divided by a negative, so we need to flip that sign now before we forget. On the left side, we get just D left. On the right side, we have negative 110 divided by negative 2.25. A negative divided by a negative is a positive. And 110 divided by 2.25 is 48.8, repeating forever. So D is less than or equal to 48.88888. So there's, once again, a summary of what we just talked about, what we just solved. How would we describe this in words? How many days will her ranch dressing supply last before she needs to reorder? So the ranch supply will last how many days? Less than or equal to 48.89. We could probably round that to 49. She'll run out on day 49, won't have quite enough. So the ranch will last up to, maybe up to 49 days before she needs to reorder. And we can write this in interval notation. Our top value is 49. We include it. Our lower value, well, this is days, right? How many days from the start of the school year? We can't go backwards in time. So 0, we could start at 0, but we can't go -1 days. That's just not possible. So we could go 0 to 49 days. Anywhere in there, if she reorders, she'll have enough ranch. 0 to 49. And that's how we represent it in interval notation. This is how we represent it as an inequality. This is an interval notation. So that covers today's objective. Given a story, I can write and solve an inequality in 2 out of 2 problems.